12-foot ladder, right? Let's just write the things we know. I have a 12-foot ladder. The base is moving at constant rate of 1 foot per second. Here's what I'm going to ask you first. So that would be given in the problem, all right? You've got a 12-foot ladder. The base is moving at constant rate, 1 foot per second, away from the wall, all right? Question. How fast is ladder moving down the wall when the base is 3 feet from wall? That's the question. So that meant, as I was pulling this away, at the moment that I'm 3 feet, right? At the moment that this distance is 3 feet, how fast was that point coming down? And then I could ask myself, what would happen, at 10 feet, right? Understand?
We wouldn't really be able to find that because we don't know where it is to begin with.
What do you mean?
How far it is from...
We know it's a 12-foot ladder. We know that the smallest this could be would be 0, right? It would be like that. And then as it came down the wall, the furthest away the bottom of that could be would be 12, right? Anywhere between 0 and 12 is fair game for me to ask how, at that instant.
But we don't know where it starts at.
It's not relevant.
Don't you need 2 sides of the triangle in order to solve that?
I don't know. We'll see. Let's see. Okay? Let's see what happens. Everyone understand the situation, how things are moving around? Understand what we're being asked for? All right. Now, again, this is an introduction to this topic. I'm just trying to get you to think about it. I'm going to give you a set of steps next class. And the first step that I'm going to give you, you don't need to write it down, just listen to me, is that you need to draw some pictures. Your pictures, I recommend you draw 2 of them. One of them is a general picture of the situation that you're looking at, with variables assigned to different parts of your picture. So here's what I call my general picture. And with the general picture, things are allowed to change and move. So I've got a wall and a floor, right? I've got a ladder in here. Where's that purple marker? Yeah. It's over there? Draw that to me. All right. I know purple doesn't come out on camera, but this is a good marker right now. Okay, there we go. We've got this ladder, right? Does the length of the ladder change? Ever? No, it's 12 feet, right? So I can label this 12 feet. This point is moving in this direction, right? And the way I could represent that point is by measuring the distance from here to here and calling it, let's say, x. Then x, right? X is changing at 1 foot per second. The value of x is changing at a speed of 1 foot per second. Do y'all understand that? And then this right here, I could label the distance from there to there, y. And that's what we're interested in is how fast y is changing, right? But that's a general picture of the situation, right? That's a general picture. We good? All right, there's my general picture. How about a picture that's the instant in question? All right. What about the instant that's in question? What's the picture look like in that instant? I'm out of room down here, so I'm going to draw the picture again. I still have the 12-foot ladder, right? That doesn't change. But at the instant in question, how far away from the wall is that ladder? is still 12 feet, right? At the specific instant in question, what? How fast is the ladder moving down the wall when the base is 3 feet from the wall, right? Yeah. That means this distance right here is what? 3. So that means x is actually fixed at 3 here. Understand? And if I know what x is, and I know the hypotenuse, then can you find what y is? Yes, you can just do Pythagorean, right? Pythagorean. Let's go ahead and do that. This will be some scratch work I do over here. I would have that x squared plus y squared is hypotenuse squared, so 9 plus y squared equals 144. Everyone following what I'm doing? All right, so subtract 9. Y squared is 135, right? And so this side right here is the square root of 135. You agree? Y is equal to square root of 135. And I'm not even going to get that on my calculator as a decimal. I'm just going to leave it as that. That's the exact value of y. Everybody understand? This is the situation you can imagine as x changes, y changes. This is the general scenario. But if I'm talking about the instant in time where that's happening, right? Yeah? Okay. Once you have written down a picture, or once you have your pictures, both of them, then what you can do next is start to write down what it is that you want and what it is that you were given. All right, so tell me what you were given in this problem. The speed of what? The ladder moving. Okay, in terms of our variables, which one of them is it? X. We are told that x is changing at a rate of 1 foot per second, yes? So I am given that dx with respect to what? Moving down, I erased it. The base of the ladder was moving away from the wall, what? 1 foot per second. That's the variable t, time, right? That's a time variable. So we're given dx dt is 1 foot per second. Understand that? The fact that it says feet per second should tell you speed. And when you think of speed, you should be thinking derivative, right? So I know that the speed of x, how fast that's moving, is dx dt. What is it that I'm interested in finding? What is it that I want? How fast this is changing, right? How fast y is changing with respect to time. So I want dy dt at a specific moment in time. I want this when?
When y is 135.
You could say when y is root 135, or you could also say when x is 3. Either way. I'm going to say at x equals 3. All right. This is the general setup right here. Are there any questions on it? You have two pictures, one of your general situation, one of the specific instant in time that we're talking about. You write down what you're given, you write down what you want. Once you have all that, you're ready to do it. You're ready to go. We good? Okay, so what we've learned in the last 2 classes is that if anybody gives you an equation, that you can always differentiate it with respect to whatever you want, right? I could differentiate an equation with respect to time, I could differentiate an equation with respect to x or with respect to y. Does not matter. I would like to try and find an equation that when I take the derivative of it, I use time as my independent variable, and I need that equation to include x and y in it, because if it has x and y, then when I take the derivatives of x and y, it'll be dx dt and dy dt, right? These things will appear. So what equation do you see anywhere over there that would relate x and y together? And when we do this, we do not look at this, okay? You never look at the instant in time when you're looking for your equation. All right, so because here's the reason why. If I ask you right now to everyone look at this picture and tell me how fast x is changing, it's not. We're fixed here, right? We're fixed. Here, x, if x changes, y changes, right? X changes, y changes. So this is the picture we want to look at. Can anybody look at that and give me any formula that you can think of that connects this variable and this variable together? X squared plus y squared is 144. Everyone agree? Pythagorean identity? That's an equation that's fair game on that triangle. So what I'm going to do now is write that down. But to recap, what I did is I looked at what I was given. I looked at this variable. I looked at what I wanted. I looked at this variable. And I said to myself, find an equation that has x and y in it off that picture. And I came up with x squared plus y squared is 144. And that's the magic equation right there. I can use that equation. It represents this physical situation, doesn't it? Let's differentiate that with respect to time. So this next step would have been find the equation. Okay, so we draw two pictures, write down what we're given, write down what we want, we find the equation. Just found it. Now differentiate it with respect to time. So what is the derivative of this with respect to time? 2x times, good, dx dt. We have to have chain rule here. dx dt plus 2y dy dt equals 0. And look at this. We have it. This is it. This is a relationship between x and y. We have dx dt, dy dt in here. Are we happy to see those? Absolutely. dx dt, we know what that is. It's 1. dy dt, hey, that's what we want to know. We have it in the equation now. That's good to see it, right? And then, do we know what x and y are? Now we can fix the moment in time. Okay, now you're allowed to come in here and fix these. So let's just plug everything in. If I go from this equation, we have 2, and then x is 3, right? I'm doing 2 times 3 times what? dx dt is 1 plus 2, y is root 135, and then dy dt equals 0. I'm going to solve for dy dt now. So this is going to be 6 plus 2 root 135 dy dt equals 0. So what would you do here? Move the 6 over and divide by 2 root 135? So that's just moving the 6 over. Now divide this side by 2 root 135. And then this by 2 root 135. And we should get a final result here. dy dt is negative 3 over root 135. And I would like for somebody on their calculator to double check to get a decimal for that. What is it?
Negative 0.258.
Negative 0.258. I forgot to put the negative, sorry. What's that? The book is going to have this answer. Okay, they're going to have this answer because that's the exact answer. But we should always convert it to a decimal just to see if it makes sense. We are not done until we put the units on here. Okay, so let me rewrite this again. dy dt equals, I'm going to use the decimal, negative 0.258 what now? Feet per second. Now look, in this problem it makes, I think a lot of people have no issue saying, yeah, feet per second because, you know, the x was changing at feet per second. The way that I recommend that you do this, if you're stuck, is to think about this ratio. Y on your picture, right? On your picture, y was this length, wasn't it? Yeah. And that was measured in what units? feet, right? And then t here is the measurement of time. And what was our time increment in this problem? Seconds. So if you take feet and put it over seconds, you get feet per second. Later on, when the problems get a little more complicated and we're doing volumes and things like that, then you might just go back to this and be like, oh yeah, this is a volume over time, and just convert your units.
So we're not going to have to do dimensional analysis?
What I'm saying is you can avoid dimensional analysis by understanding what the end result is off of this ratio. Now, if you were to do the dimensional analysis in here, let me show you. Here's what the dimensional analysis would have looked like. And some of you are going, dimensional what? Okay, so look, if I were to rewrite this, I technically should have wrote 2 times x was 3, right? 3 what? 3 feet times 1 what? dx dt, that was 1 foot per second. And then plus over here 2, and then this would have been our measurement of y, which would have been root 135, and then feet, and then times dy dt, right? Equals 0. And then what you would have done is put all this together. This would have been 6 feet squared per second, because you had feet and feet together. Then plus 2 root 135 feet dy dt equals 0. And then you would have moved this to the other side, right? And when you move that to the other side, you would have 2 root 135 feet dy dt equals 6. I'm going to write it this way, feet squared per 1 second. I'm writing that a little bit different way, negative. Instead of writing feet squared per second, I wrote -6 feet squared per 1 second. And then when I would have divided this through, right? Divided. And when I divide this, it goes away. And over here it becomes, you can look at it as division like this, 1 over it, feet. And then one of these feet cancel. And then you get your feet per second are still there. That's tedious to me. To me, that's tedious. When the end result, you can tell just by saying, hey, what was y measured in? Miles, if it was miles, you'd say miles. And if this was hours, you say miles per hour. And you don't have to keep track of all the units. Up to you.
Teach my physics class because you're much better at this.
Well, you need to know how to do dimensional analysis in physics, but we can get around it here because we know what our answer, we already knew what it was to begin with. But okay, so let me ask you a different question now. Same scenario, right? Same scenario. The ladder's being pulled away at 1 foot per second. I want to know how fast the ladder's coming down the wall when it's 11 feet from the wall. We just did 3 feet, didn't we? Right? What changes in the problem? What changes? In your instant picture, right? Your instant picture, what changes is that you're going to have 11 here, right? This is still 12. And your y changes now to be whatever that is. So 144 minus 121, 23. I think it's root 23. Is that right? It's this squared plus, we would say 11 squared plus y squared equals 12 squared. That's 144. That's 121. We'd subtract 144 minus 121. Is that 23? Yes. Is it? Huh? Is it 33? It's 23? I don't feel like writing it. What?
Actually, no, never mind. I think I get where you get the 20 square root of 23. Like
Okay, so this is 121 plus y squared equals 144.
okay, now I see it.
Subtract 121, subtract 121, that's 3, that's 2. 23 square root of both sides. Okay, so that's this, right? So that's the only thing that changes, right? Everything else is the same. We're still going to use the same equation. We're still going to differentiate it the same way. And so we're still going to be looking at 2x dx dt plus 2y dy dt equals 0, right? That's still the equation I'm going to use. The only difference is that this is what, now, 11, and this right here is root 23. So I could say 2 times 11 times dx dt was still 1, plus 2 root 23 dy dt equals 0. Are y'all following me? I'm kind of redoing the same problem, just changing x to 11.
The d whatever over dt as
Same thing, 1. The 1 foot per second, yes.
Will there ever be a problem where we're not given one of the...
No, for the most part, you have to know how one of them is changing. Yeah. So let me do this on my calculator real quick. This is going to be a different answer. Should be a bigger number. 22. So 23 root times 2. 9.59. Real quickly on my calculator, I'm getting 2.29. 2.29. Negative, sorry. I'm getting dy dt is negative 2.29 feet per second. Think about that. When this ladder, right, when it was 3 feet from the wall, that point was coming down. When it was 3 feet from the wall, the point up there was coming down at what rate? Negative 0.2 something. Why do you think it was negative? Because it's coming down? Think about this. If we had called this side y, and our answer dy dt is negative, it means y is shrinking. If it would have been a positive answer, it would have meant y is growing. So when we are 3 feet away, it's coming down at negative 0.2 something. But when we're 11 feet away, that point is coming down, what, negative 2.29 feet per second? It's actually coming down faster, twice as fast, more than twice as fast as this point is moving out. Because this is going out at 1 foot per second, right? It's coming down the wall at that instant, right at that instant. It's coming down at negative 2.29 feet per second. It's actually at negative 2.29 times faster.
You said coming down, which was like 0.2.
Oh, yeah, okay, sorry. Fast. I was talking about faster than the rate at which I'm pulling it out, not faster than the rate initially, yeah. All right, does this kind of make sense?
Yes.
All right, so we are going to be doing problems next class where we're going to be working with circles that are growing at a certain rate and trying to figure out how the radius and areas are connected. We're going to be doing spheres that are growing at certain rates. We're going to be doing, well, watch the video. You'll see. We got airplanes flying overhead. We've got people walking away from light poles and how their shadows are changing. And we've got all sorts of different things. And so it should be an interesting class. Anything else? Finish up your homework for 2.6, implicit differentiation.
That was clever.